Section 3.6 is the chain rule, so another derivative rule that will be useful for us. And I'm going to let you work through this quick review. I'm going to give you an option. This is composite functions. If you are at all shaky on composites, please do some of these. If you feel super confident with your composite functions, you can just go through or try one or two. But the idea of a composite function is something that we are going to be using in the chain rule. So I want to make sure you're confident. So I'm going to scroll through these slides, pause and do each one if you would like, and the answers will pop up as well. So here are the first 5 problems. Okay, here are the next 5 problems. Again, pause and work them. Here are the answers to the first group, and there's the answers to the second group. If you have any question about this, be sure to ask me at the beginning of class. Okay, the chain rule. So write this down and then I'm going to go through it. If f is differentiable at the point u, which is equal to g of x, and if g is differentiable at x, then the composite function f of g of x, written both ways, is also differentiable at x. And f of g of x prime, the derivative, is f prime of g of x times g prime of x. So we're taking the derivative of f at g of x and then the derivative of g of x. So it's important to know what your inside function is, in this case g of x, and what your outside function is, in this case f. Using other notation, if y equals f of u and u equals g of x, then dy dx is taking dy du, the derivative of the outside, times du dx, the derivative of the inside. And you notice that these actually work like a fraction. Dy dx is dy du times du dx. Those would cancel to get us our dy dx. Okay? Let's do a couple of these, but get this into your notes. So, derivatives of composite functions. An object moves along the x-axis so that its position at any time t is greater than or equal to 0 is given by this function. Find the velocity. So remember, the velocity is s prime of t. Now, s of t is a composite function. One way to look at it is like this. It's a composite function where s is the sign of u, and u is 5t minus 3. So using my notation, I'm going to first find ds du, the derivative of s with respect to u. The derivative of sine u is cos u. And then du dt, the derivative of u with respect to t, is just 5 using our power rule. Then to find ds dt, which is what I originally wanted, ds of t, ds dt, I'm going to do ds du times du dt, which is cos u times 5. So that's ds dt, but remember, I want to put this back in terms of t, so I'm just going to substitute my original breakdown. U was 5t minus 3. I'm going to substitute that back into my composite. So that's using the Leibniz notation. I want to also talk about this using this. So if y is f of g of x, then dy dx is f prime of g of x, don't change this, times g prime. In words, we say differentiate the outside function f and evaluate it at the inside function left alone. We're not going to change g of x the first time. Then multiply by the derivative of the inside. So let's look at the one we just did using this kind of thinking. S of t was sine of 5t minus 3. So s prime of t is the derivative of the outside. The outside function is sine. The derivative of sine is cos. I'm not going to do anything to the inside. That's f prime of g of x. I'm going to multiply that by the derivative of the inside. The derivative of 5t minus 3 is 5. So I end up with the same answer. It takes a few less steps, but it also takes a little bit more thinking. It's not quite as concrete and broken down. So we're going to talk about doing this both ways in class. At some point you will come to a decision as to which way is best for you. So outside, inside. Differentiate cos of 3x to the fourth minus 2 with respect to x. My outside is cos of, well, it's the cos function. My inside is my 3x to the fourth minus 2 function. So d dx of cos of 3x to the fourth minus 2 is the derivative of the outside. The derivative of cos is negative sine, leave the inside alone, times the derivative of the inside. And normally we're going to put our coefficients in front, and there's my final. Alright, sometimes the chain rule needs to be used more than once. Let's look at this. There are 3 different functions here. I want you to see if you can determine, before I tell you, what the outside function, the middle function, and the very inside function is. So take a look at it and see if you can figure it out. Alright, rewriting it this way helps a little bit. So taking that cube root and writing it as a 1/3 power so we can use our power rule. So my furthest outside function is something raised to the 3rd power. My middle function is the sine of something, and my inside, my very inside is the thing that's inside of, stop it, is my x squared. Alright, so the derivative of the outside, leave the inside alone. So 1/3 comes down, that doesn't change, my power is subtracted by 1. So that's my derivative of my 1/3 function. The next one I have to take the derivative of is my sine. So derivative of sine is cos. Again, don't touch that inside function. And the last thing is to differentiate my x squared to 2x. So 3 parts. The first is to take the derivative of the power, 1/3, don't touch anything inside, raised to the negative 2/3. Multiply that by the derivative of sine, which is cos, but don't change the x squared, and then finally the derivative of the x squared. Yeah, they just brought the 2x out front, combined it with the 1/3 to make things a little bit cleaner. Ooh, that was quickly to the end. So the chain rule is a bit confusing. We are going to work on it quite a bit, but you might want to go back and look at a couple of these examples again, and I will work an example in class for you as well.